So for the video, we start a new lecture now. Also. So, okay, let's continue. I just said we'll look a little more about, we'll talk a little more about premixed flames. And we just talked about the dynamics of the flame, what is the burning velocity, and how is it impacted by, stretch, curvature, and strain. And then we looked at, how can that lead to instabilities also. And now we want to look a little more at the flame structure. We'll start out here by what's called the thermal flame theory. Why is it called the thermal flame theory? Because we assume one-step global reaction. So, there's no more complex chemistry. And we'll see later on that that's actually not really right. But the analysis that was done is a very classical analysis. You see here, this theory says here, this theory is the origin of a development which placed combustion science on a mathematical basis. Okay, so this one is some very early work here, 1938, where people didn't have a computer. They also didn't have laser diagnostics and all of this. They just had the governing equations and they had a pencil. And that's all they had. And they could, and that's, so it's very interesting to see how people at the time really use their brain to understand what's happening. And so we want to walk on these, want to walk on this path and try to understand. And the result, even though we said maybe it's not exactly right, because we'll see later on what the effect of multi-step kinetics is, even if it's not exactly right, it will still tell you a lot about premixed flames. Okay, so the idea here is we start out with a stationary flat flame front as we discussed it earlier. And the idea here is really we want to have an algebraic and analytic relationship for the burning velocity as function of the governing parameters. And this, we looked at earlier here, Frank and Kamenetsky, Zeldovich and Frank Kamenetsky, they made these assumptions that I mentioned here earlier. They say we have fuel and air, we have a preheat zone, and then there's a temperature here at which chemistry starts, and then that converts the temperature and also the species mass fractions to equilibrium conditions. So they make the assumption that there are three zones. Zone number one is the preheat zone. Zone number two is the reaction zone, is this gray part. And then behind the reaction zone, we have an equilibrium zone. Okay? Equilibrium zone, you see already, is trivial. We know already how to compute equilibrium. And the temperature and species mass fractions, they're constant there. So that's relatively easy to understand. The other two zones need mathematical analysis, and that's what we then do next. So this all I explained to you earlier. You have this is how this premixed flame works. You have hot equilibrium region. From this hot equilibrium region, you have a heat flux into the unburned, which heats up the unburned gases, heat them up to a certain temperature where chemistry starts, and then you have these reactions, and they then lead to conversion of the species mass fractions to their equilibrium constants. So that transition happens at this point. We call this point xi, and we call the temperature Ti, T ignition, or whatever the I stands for. Let's say ignition, and so that's an important point. We make the assumption that we have one-step global chemistry, fuel and oxygen and so on, and we have the reaction rate then, which is given by B pre-exponential factor times concentration of fuel, concentration of oxygen, times exponential of minus E over RT. And then behind the flame front, we have the equilibrium region. I said already this is kind of trivial. The reaction rate is 0. In the equilibrium zone also the fuel and also the product of fuel and oxygen is 0, because for lean flames the fuel would be 0. For rich flames the oxygen would be 0. Okay, so that's the equilibrium zone. And then we have coupling functions. If we assume specific heat is constant, we assume constant enthalpy of reaction, and we assume unity Lewis numbers, then we can derive these coupling functions between mass fractions and the temperature. And this shows you that the 3 unknowns I have, or maybe I have 4 unknowns, the temperature, the oxygen mass fraction, fuel mass fraction, and the product mass fraction. Product mass fraction doesn't appear somehow, so I don't really need it. It doesn't appear in my reaction rate, so I need only these 3, and because I have 2 coupling functions, I can all reduce it back to a temperature equation. Okay, I need only 1 equation. That's already pretty good. We use the low Mach number limit, constant pressure. And this is all clear anyways. We said earlier continuity equation can be integrated so that rho V is equal to rho U times SL. And then I can write the temperature equation like this. I have the convection term, I have the diffusion or the heat conduction term, and I have the chemical source term. Okay? And the assumption now is, and that actually is a pretty good assumption, the assumption now is that the preheat region, in the preheat region there's no chemistry, so the chemical source term is 0. So the equation for the preheat region is just these 2 terms. Okay, that's obvious, that's easy to understand also. Okay, you say there's no chemistry, then it's obvious. The second assumption is that if the temperature is higher than this ignition temperature, we are in the reaction zone, then the reaction zone is governed only by these latter 2 terms here. The convection term is small compared to these 2. That's a little harder to understand because you have a flow that goes in the reaction zone. But if you ever do simulations of such a preheat flame and you numerically evaluate these terms against each other, then this is exactly what you see. These guys, they didn't have a computer to try this out. They were just thinking, look, I have in the flame is very thin. I mean, look again. I mean, that's what they had. They had a little Bunsen burner or whatever, so they could look at the flame and they thought, look at this flame is so thin. The gradients must be so large that these gradients must be very large compared to, or the second derivative must be very large compared to this gradient. And so that's exactly what happens, is that this first term here is small. So in the preheat zone, we have a balance of these 2 terms. In the reaction zone, we have a balance of these 2 terms. So we can start out, looking at the preheat region. That's what we do first. So the preheat region, this is the equation. Rho U SL is constant. And you see if rho U SL is constant, I can directly integrate this. Okay? So the boundary condition here is that at x equal to infinity, the gradients must vanish. The gradients must vanish. And then I can integrate this, and you see the integration of this gives me lambda. So if I integrate this from minus infinity into the flame to some point x, let's say, then I get lambda over Cp times dt dx at that point, minus lambda over Cp dt dx at infinity, which is 0. Okay, so that is this term. And then on the other side, you get t minus tu. Okay, t at minus infinity is tu. That is this term. And then we have this coefficient here, lambda over Cp. lambda over Cp, and rho u as L. Okay, so that's already a nice relation. You see that if let's say I assume that all this to be constant, this coefficient, then I can further integrate this directly. I can directly get the temperature as function of x in the preheat region. And what's the function of this? If you integrate this in your mind, dt dx is equal to a constant times t, gives you what? Gives you an exponential growth, okay? In the breaks, I don't get the time to go and get coffee because of all the questions, and so I didn't drink in the first hour. I realized my voice is going away. So I need to drink maybe tomorrow. I don't mind, not going there. Maybe somebody can bring me a coffee and a bottle of water tomorrow, but not everyone. Maybe. Okay, so this is an exponential growth. So if we go back to this simple picture here, this is an exponential growth. Okay, we know this now already. We can see this roughly if we assume this constant. So, but this is the result we have. We can evaluate this at the ignition point. Okay, that's what we always do in asymptotics. Asymptotics is a funny business. You have this point xi, and you say, on this side I have the preheat region, on this side I have the reaction zone. The preheat region is only governed by these two terms, and the reaction zone is governed by these two other terms, okay? Which means at xi, all terms must be important somehow, you would think. But now we assume at xi, if I come from the left side, this is the solution. And we'll see later, if we come from the right side, then the other two terms only the other two terms are important. Okay. Anyways, this gives us a relation between the gradient at the ignition point then and the temperature. That's what it does. Okay. Okay, so second assumption, or now we look at the reaction zone, and the reaction zone is governed by the heat conduction term and the chemical source term. So this is now a little more difficult, but the first thing we'll do, and then you will see we're almost there. The first thing we do is we have this d by dx here, and we want to replace this by a d by dt. And we can do that because it's a one-dimensional configuration. T is just a function of x, which means I can express a change with respect to x. I can also express it with respect to temperature, okay? Because t is a unique function of x, or x also is a unique function of t. If the temperature would go up and down like this, then we can do this. But because the temperature only goes up, x is a unique function of t. So the d by dx here, we write it as dt by dx, d by dt, okay? We can do that, and then you see this is a dt by dx, and then here we have a dt by dx, so I can bring this inside, and I get d by dt of lambda over Cp dt by dx. Okay, you see this? Now if I differentiate this again by chain rule, this would be 2 lambda over Cp, this goes away, the 2 lambda over Cp goes away, times dt by dx, which is this, times dt by dx of this, okay? So, so this now is function of temperature, and you see I can integrate this in temperature. And the right-hand side here also is only a function of temperature. And it's a little more complicated function of temperature, but I can also integrate that in terms of temperature. So the next thing I do, I integrate this in temperature from T, any point in the reaction zone, and we'll say we integrate it from Ti all the way to Tb, okay? Through the entire reaction zone into the equilibrium layer, okay? So then you see, this is what we get. You see here on the right-hand side, we say this here is not a function of temperature. We also said Cp is not a function of temperature, so this is lambda times omega. So we have the integral of lambda times omega from T to Tb, where we want to evaluate this here really from Ti to Tb. Okay, and then this is we said this is constant, and then here on the other side, you see that if we integrate this, we get this here evaluated at infinity, where the gradient is 0, minus this here evaluated at Ti. Okay, and this is this gradient here evaluated at Ti. Okay, so that's almost analytic, except, and then because here we had a square, here we have the square root. Okay, so this step is relatively trivial. What's a little harder is to evaluate this integral. Now the next step. So now we have a solution that governs the preheat region, and we have a solution that governs the reaction zone. And we have a solution, both we have a solution for this gradient. And you see now, I can have, if again I look at my simple picture here, I have a solution for this gradient that comes from the preheat region. I have a solution for this gradient that comes from the reaction zone. And now, this is also very typical in asymptotics. Now there is what's called a matching condition. At this point, if you go from the reaction zone and you go to basically minus infinity, or you go to from the preheat region and you go to plus infinity, or you go to this point Ti, then the gradients, they must match. Okay, that's the matching condition, which means we can set the solution we got in the preheat region here. We can set that equal to the solution we got at xi. We can set it equal to the solution we got from the reaction zone. That's the matching condition. And then we'll see that this will give us a relation for the burning velocity. Okay, so that's where the eigenvalue again comes in. There's only one value of SL that will satisfy this matching condition. So first of all, what's a little hardest is to evaluate this integral of the reaction rate, because here we have YF, which basically includes by the coupling function, this is temperature, this is YO2, also by the coupling function, this is temperature, or it's TB minus temperature, and then here we have E to minus E by RT, temperature, very nonlinear, and it's hard to integrate this. So what we do here is we do a series expansion just of the argument of the exponential function minus E over RT. We do a series expansion around TB. So this will be this function evaluated at TB plus the derivative of this minus E by RT squared, or it's in plus E by RT squared evaluated at TB times T minus TB. That's just simple series expansion, Taylor series expansion, and we just keep the first two terms, and then now it's linear in T. Okay, so we can we define now a non-dimensional temperature, E times T minus TB divided by RT squared. That's a non-dimensional temperature, which really tells us the difference, the departure here from TB. And so if we use that, then we can write the reaction source term as this coefficient times this here comes from the series expansion. This is then the linear term from the series expansion, and this is the coefficient here with a theta and theta squared, which comes from inserting from the basically the fuel and the oxygen mass fraction, inserting the coupling function. So this is something we can integrate. So this is just this integral. If we integrate this, then this is what we get. Okay, and this doesn't look too simple, but at least it has been integrated. Okay, now we make a few more assumptions. That's again, asymptotic assumptions. What we assume is that the activation energy is very, very large. If the activation energy is very, very large, then a term that is exponential function of Tb is much, much larger than exponential function of Ti, because activation energy very, very large means if the temperature is reduced by just a little bit, the reaction rate becomes very, very small. And so we substitute the theta I. We say because theta I is smaller than theta B, so we might, because it's the reaction rate resulting at that point is so small, we might as well replace it by theta U. Okay, so that's the theta I are then replaced by theta U. That's the first thing we do, and then we say that theta U is so small. This term is so small, we might as well replace it, the theta U, by minus infinity. Now you would say, well, there is no, minus infinity temperature, but the theta here, but for asymptotic reasons, this is small, and exponential function of minus infinity would be 0, so we just make it minus infinity, so these terms disappear. So this one goes away, this one goes away, and what's left over is just this term. And this term is interesting. So we can, if we just have this term, we can equate it then with the, or plug it in this relation, and then this is what we get. This is what we get for the preheat zone. This is what we get, and now we can equate these two, and you see that here in the, or sorry, I should say this. In the preheat zone, the solution was actually Ti minus Tu, okay? But from the view of the preheat zone, for large activation energy, Ti is very, very close to Tb, okay? So we might as well replace it by Tb. So we replace Ti by Tb, and then this is what we get. Now we can equate these, and then equate this, and then you see we can solve this here for SL. If we do this, then this is what we get, where we have here a factor that we'll look at in a little more detail. Then here's an exponential function, which we would expect, and then we have this S factor. S factor here has YO2 in the burned, Y fuel in the burned, and it has this third term. And the S factor, really what it means is, if we look at the lean flame, then lean flame means fuel would be 0 in the burned, and then the first term here is the large term. The other two terms are small. If we look at rich conditions, then this term is small, and this term is large, and this term also is not very large. But if we look exactly at stoichiometric conditions, then both O2 and fuel would be 0, and then this third term here remains, okay? So that term S, it just switches between lean, rich, and stoichiometric conditions. This is a little different from the original analysis, which considered first and second order kind of reaction equations. But anyways, that's what this term does. Yeah, that's what this here says. So so in summary, this is what we did. In the preheat zone, we neglected the reaction rate. In the reaction zone, we neglected the convection term. Then we were able to get expressions here for the gradient at this ignition point. The one issue was integrating the reaction rate. So we used a series expansion to make the argument of the exponential term linear. And then we evaluate material properties here at TB. Because for large activation energy, TI is very close to TB. And then we evaluate the integral between minus infinity and TB, which then simplified a few terms. And in the preheat region, we set Ti to TB. So if you think about what does the assumption of infinitely large or very, very large activation energy do? What it does is it makes the Ti very close to TB, but at the same time, the exponential function of TB is much, much larger compared to the exponential function of Ti. Okay? So Ti and TB are very close together, but the exponential function of these two arguments is very, very different. Okay, that's what the assumption of large activation energy does, and because of this, the chemistry always takes place at a very high temperature. If you decrease the temperature by a little bit, no more chemistry. Okay, because the exponential term gets very small. Okay, so this I just mentioned. This S factor is a little different from the original analysis, but that's what it is. This just summarizes, again, the expression we get. So the expression here, the reason why I go so quickly over this is because I said in the beginning, you know, maybe it's not exactly right. There's some other things that matter for multi-step chemistry. But what's interesting is that you can now look at these, you know, the mathematical relation and try to understand what are the values, what are the quantities that affect the burning velocities, and in what way do they do this. And we want to do this by analyzing now characteristic scales of the flame, like characteristic velocity, you know, diffusivity, flame thickness. All of this can be analyzed from or determined from analyzing this term. Okay, so the burning velocity we said is an eigenvalue of the system, and but it somehow must be influenced by both the transport in the preheat region and also in the reaction zone, and also by the chemistry. Okay, so the chemistry has a time scale, and because we assume one-step global reaction, there is only one chemical time scale, which means that if we look at this, or if we want to just intuitively, we want to develop a scaling for the burning velocity, then if it's an interaction of transport, which is governed by the diffusivity, and chemistry, which is the parameter is a time scale, then SL has to be by dimensional arguments. It has to be the square root of d divided by t, by the time scale, chemical time scale. Okay, that's just dimensional analysis, saying these are the two important parameters. Okay, so then we can also look at the how these are defined. The diffusivity here is defined as lambda over rho Cp. That's the heat diffusivity. And then we can also, so this what we just had, and then we can also define, from these two parameters, we can define a flame thickness, thickness of the flame, which is then d times dc and the square root of this. And from this, SL or LF divided by SL, that should be a time scale, a flame time scale, and that then would be equal here to the chemical time scale. That's interesting because the chemical time scale is the time scale in which reactions happen. The flame time scale is the time over which the flame propagates by one flame thickness. Okay, so that's what this time scale is, and apparently these, from simple scaling, they should be related. Now, if we look at the expression we just derived here for the burning velocity, you see there's a very similar structure. SL is the square root, we just said, of d divided by Tc. D is lambda over rho, bring the rho here to the other side, lambda over rho Cp. That's the heat diffusivity, which means all the rest must be the chemical timescale. Okay? So the chemical timescale is this entire thing except for the lambda over rho Cp. Okay? So that's the chemical timescale. Okay? And I can write this now. I can write this as here 1/2 times rho u divided by rho b times the Zeldovich number we defined earlier, Tb minus Tu squared divided by Tb minus Tu divided by Tb. That was the heat release parameter, times E divided by RTB. That was the non-dimensional activation energy. And you see that parameter appears here squared. So Zeldovich number squared times here this factor. Now what's interesting is that usually when we have a chemical reaction, so chemical reaction, let's say, is A plus B, or well, we say fuel plus oxidizer goes to products. Okay? And I want to know the chemical time. So this has a reaction rate, which is equal to B times the concentration of fuel, concentration of oxidizer, times exponential of minus E divided by RT. Okay? And if I want to know the time scale of this, then I would say the time scale, chemical time scale, let's say to the -1, would be omega divided by Cf. Okay? That omega has units, units mole per cubic meter second. And so this ratio has units 1 divided by time. And this, in effect, is the time it takes. So if I look at the equation, so let's say I had an equation, a homogeneous system, dCf by dt is equal to omega. And then if I make this non-dimensional, I could say, I could bring this, divide the whole thing by Cf0, okay? The initial concentration of fuel, and this is non-dimensional, here chemical time, and then you see I just get a non-dimensional, so this here divided by Cf, that gives me the time scale, that the time in which the fuel concentration changes by order 1. That's the time scale we defined like this. So that is exactly this here. This is B times the concentration of oxidizer times the exponential term. That's how we would define the time scale. But what we found now from the analysis is that the time scale is this times the Zeldovich number squared. Okay? And that's interesting because that number is typically of the order of 100. So the time scale we get is not the time scale that we would define in a homogeneous system, but because the transport causes certain conditions in the reaction zone, the time scale here is about a factor of 100 different, okay, from the from what we would typically define, okay. So that is because the diffusion, you know, makes the concentrations very small in the reaction zone. Okay, so the chemical time scale for a premixed flame is not only determined by chemistry, like in a homogeneous system, it's also determined by the flame structure. Okay, so then we can define here this flame time. We did this earlier. SL, then this we defined already. This here we defined already. And this chemical timescale here we defined already. Now we can think about how can we define the flame thickness. For now, flame thickness was defined only by scaling, but we can also have a rigorous definition. Actually, this relation we had from the preheat region, that really helps us also to define the flame thickness, because you could say, so this here is this gradient at the ignition temperature, okay? And we could say if we extend this to TB and to TU, then this should be the flame thickness. That's a rigorous definition, and you can do this here. So this would be, assuming this is linear, so I can replace dt dx by TB minus TU divided by LF. And because that is equal to this is what we had earlier. This was the solution of the preheat region. Then I can, you see TB minus TU goes away, and I can solve this for LF, and I get this, okay? So LF is lambda over CP rho U SL, which is what you would usually use from scaling analysis, is consistent with the solution, the exponential solution that we had in the preheat region. This assumes that the preheat, the flame thickness, is essentially the thickness of the preheat region, and the reaction zone is very thin compared to that. So the reaction zone, the preheat region plus the reaction zone is almost the same as the preheat region itself, okay? So that's an assumption that we always make, and that's also numerically, if you evaluate it, that's a pretty good assumption. Okay, so let's see. We have a little more time. So then we can talk about any questions up to this point? So then we can talk about the effect of finite rate chemistry. How does finite rate chemistry affect the flame structure? And for that, we first want to look at so we want to use methane air combustion as an example, and we'll see later on that all other hydrocarbons are essentially very similar. Not exactly the same, but much of the analysis would be very similar. So far, we have looked at one-step global reaction, and then everything is only controlled by temperature sensitivity, which is why this large activation energy was so important, but there's no chemistry really involved here. In contrast, if you do numerical simulation, you can look at detailed chemistry, but you get a result, and it doesn't tell you very much. I mean, the analysis really tells you what's going on. So we want to look at a methane mechanism, or mechanism for methane air combustion, very simple mechanism, that will be reduced to a four-step mechanism, which has only the four most important steps. And then, the analysis can be done with these. And these four important steps, they tell us always also, they tell us a lot about the structure in a real flame. So for that, let's first look quickly, because now we want to look at finite rate chemistry, detailed chemical kinetics. Most of you take this or many of you take this in the afternoon from Professor Pilling. But I want to give you just a few things that I think are important for when we think about chemistry. So this lists here 4 different types of reactions. You look at a reaction mechanism, it's always important to understand the type of the individual reaction. And the nice thing about hydrocarbon chemistry is very easy to understand. I mean, a lot of people are scared of chemical kinetics, but combustion chemistry is really not the stuff that Professor Pitting does, the stuff that we are talking, it's very simple. I mean, it's very easy to understand, okay? So you have initiation reactions. Let's say you have a fuel-air mixture in the beginning. You have nothing else than just fuel and air. Then, or oxygen, you have to have some initiation. Reactions have to start somehow. This could be, for example, here, thermal decomposition. Methane goes to methyl plus H, which happens only at super high temperatures, okay? At lower temperatures, you might have something like fuel plus oxygen, okay? So, for example, methane plus oxygen goes to methyl radical plus HO2 radical. That's another initiation reaction, or this is an initiation reaction, okay? These reactions only happen, they're only important under either very high temperature conditions. In diffusion flames, this can be important, or it is important under conditions where you have no radical whatsoever, in the very beginning of an ignition process. But in flames, typically, you have radicals, and because you have radicals, you know, reactions like this are not that important. Reactions like this are much more important. Methane plus radical goes to methyl plus H2. Could also be methane plus OH goes to methyl plus H2O, okay? There are three important radicals, H, OH, and O. And so these are the ones that, you know, do all the work. And for most purposes, it doesn't really matter which one exactly, you know, does the work. Then the most important thing when you look at a chemical mechanism is to understand the radical balance. That's really the most important thing. So whenever you look at a reaction, think of radical balance. If I ask you, what can you say about this reaction? Don't say, well, it has a methane on the left side and it has this other thing on the right-hand side. Count the radicals. No radical here, 2 radicals here, okay? This produces radicals. That's the right answer. This one here, it's radical neutral. No change in number of radicals. See, this is why it's in red here even. This reaction here now is a chain branching reaction. It increases the number of radicals. H2 plus O goes to OH plus H, okay? Actually, that's the wrong reaction here. Forget about this. I'll show you another. This is not chain branching. If you look at the standard textbook, that's why it's here. Standard textbook would tell you this is chain branching reaction. In my world, it's not chain branching. Why not? Okay, let's move on, and we'll come back to this. Chain breaking reaction. 2 radicals on the left-hand side, no radical on the right-hand side. That takes out radicals. Here, I have radicals on the left-hand side, fewer number of radicals, a smaller number of radicals on the right-hand side. This takes radicals out. These are the most important reactions. They govern everything. If you have a reaction that produces radicals, it makes from one radical, it makes 2, okay? Which means this reaction will now be twice as fast. So it will make 4. It was 4 times as fast, it will make 8, and so on. So chain branching reactions always lead to exponential growth in the number of radicals, which means explosion. That's when things really go wild, okay? And chain breaking reactions, they do the exact opposite. They take out radicals, make combustion slow. Ultimately, they lead to extinction. If you don't understand combustion chemistry, these are the 5 rules you need to know. And then combustion chemistry is very, very easy to understand. Number 1, reaction progress is mostly determined by radicals. It's all about the radicals, okay? Number 2, the radical balance is then the most important aspect. I just said that. When you see a reaction, immediately in your brain, it should say chain branching, chain breaking, or neutral. Most reactions that you see are chain propagating, meaning they're radical neutral. They just convert something from larger to smaller. Next reaction, larger to smaller. Nothing happens with the radicals. They just do progress in going from maybe a large hydrocarbon molecule down to smaller molecules, CO, and then CO2. But they don't do much with the radicals. They're not so important. They're They just do a little labor, but they don't change the dynamics. But there are a few that are chain branching or chain breaking, and these are the most important. Okay, so that's what you need to watch out for. The most important radicals are H, OH, and O, and for radical poor situations also HO2. It's during ignition. Why HO2? Because fuel plus O2 gives HO2 plus fuel radical. So, you know, under radical poor conditions where you basically only have fuel and oxygen, that's what would happen. These are the 4 rules, and if you look at this, it all says the same thing. Every rule says the same thing. It basically means, you know, look out for radicals, okay? So there's one more rule, and that is that the O radical counts twice. Why does the O radical count twice? It's just twice as important as the others, twice as strong, and so on. You could argue here with what's called the fast shuffle reactions. There are some reactions here. O plus H2 goes to OH plus H. OH plus H2 goes to H2O plus H. And 2OH go to H2O plus O. These reactions, they're always, under combustion situations, they are in partial equilibrium. They're basically in equilibrium, which means if I produce one more O radical, then the equilibrium will take this O radical and convert it partly to OH and H. Okay? If I add OH radicals, this reaction will go the other way. So these fast shuffle reactions, they go forward and reverse very fast all the time. Okay? And they just equilibrate the concentrations of OH, H, and O. Okay? So, and what you see here, that if that's the case, then an O radical is always worth 2 other radicals. O radical is worth 2 other radicals. Here OH is worth 1 H radical, but here again 2 OH are worth 1 O radical. An O radical always gives you 2 of the other radicals. Go back. Why is this not a good, I asked the question earlier and I promise you come back. Why is this not a good example for a chain branching reaction? Exactly. I have 2 radicals on the left side and I have 2 on the right side. Now, don't get confused. When you look in the standard textbook, they just count the number of radicals. 1 here, 2 there. This is why in the typical textbook you would find this chain branching. But I think it's not exactly right. I think O radical is twice. It always gives you twice 2 of the others. And so this is not chain branching. This is radical neutral. What is a good example for chain branching reaction? Or in other words, what's the most important chain branching reaction in combustion? Good. I'm glad I'm telling you this. There are 2 reactions in combustion that you should know. All the others you can forget. Don't tell Professor Pilling I said that. We'll get to that point. O radical counts twice. Fast shuffle reactions are important. Now, this is the mechanism we want to look at. You see here forward and reverse reaction are specified independently. Bad, you shouldn't do that. I mentioned this earlier. This will give you the wrong equilibrium constant if it's not absolutely consistent. And then here you see number 2, 3, and 4. These are the fast shuffle reaction I just mentioned. And then here number 1, that's why in this mechanism is number 1. That is because this is the most important chain branching reaction. And because chain branching, that's the most important thing. This is the most important combustion reaction, period. Okay? O2 plus H goes to OH plus O. What does it do? On the left-hand side, I have 1 radical. On the right-hand side, I have how many radicals? 3, very good. So it takes 1 radical, and so every time it's executed, it produces 2 new radicals. Okay? That reaction is not fast or in equilibrium or anything. Actually, you see, you break up here the O2, but if this is executed, you will produce radicals. You will make more radicals, and this can, be executed again, and so on. So this leads to exponential growth. The other one that's very important is here this reaction 5. Reaction 5, you see it almost has the same reactance. O2 plus H is the same as the chain branching reaction. O2 plus H plus M, but now this goes to HO2 plus M. It's a recombination, or it's not recombination, but it's a combination of O2 and H. So you get HO2. This is still a radical, but it turns out that this HO2, it really likes to do these things here. HO2 plus H goes to H2 plus O2. So this is two radicals. This is no radical. So this here, this reaction is actually, or also this here, HO2 plus H goes to H2O plus O. It really likes to do these things. So as soon as I execute this reaction 5, I get HO2. And if I'm not, if it's not during ignition or something where this HO2 radical could be important, then it leads to chain breaking. Okay? So this is the most important chain breaking reaction. This is the most important chain branching reactions. These are the two reactions that you should remember. There are a lot more reactions here. You know, here, for example, you have the methane reactions. We'll talk about methane combustion. I think here this reaction 38 is one that pops up later. I said this is in the premix flame is the most important consumption reaction for the methane molecule. But you see one radical here, one radical there. So this also is a chain propagating reaction. It doesn't really produce any radicals. Okay, so you see here, this has also C2 species, C3 species, and so on. Okay, so this is then taking this chemical mechanism. This is how the flame looks like. This is the H mass fraction, and you see the H goes to, radicals go to 0 here at roughly 2 millimeters. Below the, well, here, whatever 2 millimeters means, but below this point, or this is the unburned here, this is the burned. This here is the temperature, maybe I should have said that. Here, if I go from below this point or towards the unburned, there are no radicals, okay? And you see the temperature here is about 1000 Kelvin, where the radicals go to 0. So that, what we called earlier the ignition temperature, that's about, let's say, 1000 Kelvin. Then here you see here the increase of radicals is very, very strong, very fast. And then you see this here then goes to the towards equilibrium. It's not reached here yet, but it goes towards equilibrium. Here you see you're getting very close to equilibrium. This is again the temperature. This zooms out a little bit. You see this goes from 1 to 3. This goes from 1 to 5. And then you see here that in this region here where I have a lot of radicals, I convert the fuel to CO. So this is the maximum of CO. And then the CO goes away and CO2 appears, which means I convert the CO. The CO is oxidized to CO2. So here really we want to distinguish 3 different regions, or maybe one could say 4 different regions if you also count this equilibrium region. We have the preheat region where you have no radicals and no chemistry. Then we have the reaction zone, or what we call the inner layer, where radicals are being produced. The fuel is consumed and converted to CO. And then we have the oxidation layer where the CO is converted to CO2. And you see that's again a thick, that's a wider region. The inner layer here is actually a very small region. Okay, so let me see. We have a few more minutes, and let me see where this here takes us. Maybe I'll show you this real quick, and then I will do the same thing tomorrow in the beginning, because maybe this is the most important thing that I tell you here about premix flames. I just mentioned that these two reactions, they're the most important reactions. This is the most important chain branching reaction. This is the most important chain breaking reaction, okay? So if a flame burns or not depends on which one is faster. If chain breaking is faster than chain branching, then flame will extinguish. If chain branching is faster, flame will burn, okay? So which one is faster? It has to be branching, otherwise it wouldn't burn. That's a good point. But the answer, of course, is it depends. Okay? It depends on the conditions. What's interesting is, and I will show it to you on the board, what's interesting, it's pure coincidence of nature that both of these reactions almost have the same reactants. Okay? So I can evaluate the ratio of the reaction rates. If I want to know which one is faster, I can just evaluate the ratio of these reaction rates. If the ratio is larger than 1, then chain branching is faster. If the ratio is smaller than 1, then chain breaking is faster. If this is larger than 1, flame will burn. Smaller than 1, flame will extinguish. Okay? So what is omega 1? The reaction rate 1 is K1F, let's say, times the concentration of O2 times the concentration of H, and that's it, okay? Divided by omega 5 is K5 times concentration of O2 times concentration of H times concentration of the third body. Concentration of the third body, let's say it's the total concentration, which is P over RT. Then you see here, these concentrations, they go away. And the ratio is K1F by K5 times Cm, okay? Or I could replace the Cm by P over RT. Then I have here K1 F divided by K5 times P over RT. So that's it. I mean, isn't that interesting that this ratio, which I say is the most important ratio of two different rates in combustion, is such that the concentrations go away. This is independent of the concentrations of the reactants. Okay? That's beautiful. This is usually where the students have tears in their eyes now. I don't see anyone crying. But don't you share this enthusiasm for nature? I mean, this is where you think this was done on purpose. Somebody did this on purpose. Anyways, it's very nice. So this is what it is. Now we can plot here, for example. I mean, we can evaluate this quantitatively. This is only a function of temperature and pressure. If you give me a pressure, I can compute the temperature for which the ratio is exactly equal to 1. And if the temperature is larger, then one is faster, and if the temperature is lower, the other one is faster. So we can do this graphically. Look at so this is an Arrhenius plot, where we plot the log here of the rate coefficient as function of 1 over temperature. And so it turns out this K1 has an activation energy of 70, roughly 70. And this here the activation energy is almost 0, actually slightly negative. So this is K1, this is K5, okay? And you see, this is not K5. K5 has different units than K1. You cannot compare K1 and K5 because K5, reaction 5, is a trimolecular reaction. K1 is a bimolecular reaction. So this is K5 times the concentration of the third body. So here, this is for a given pressure, 1 bar. For different pressure, this line would be different. And then here you see for high temperatures, this is faster. For low temperatures, this is faster. And there's a so-called crossover or inner layer temperature, which is given here, just by this relation, comes out to be roughly 1000 Kelvin, which is exactly what we saw of course, real life is a little more complicated. There are other reactions that contribute to the radical balance. But even this simple expression here, it gives us a temperature, you know, that's roughly what we saw in the detailed numerical simulation. So temperature is high, it can burn, but at low temperatures here, this thing, it doesn't burn because K5 is larger than K1 at atmospheric conditions. If you take a flame and you bring it to a temperature below roughly this, let's say, it will extinguish. The flame will go away. One-step chemistry doesn't know this, by the way. Only multi-step chemistry knows this. Okay? So with this, contemplate over this, the beauty of the, you know, how beautiful the chemistry, the physics are. And so I'll let you go and wish you a good day and see you tomorrow.